Hello everybody, and welcome back to another geometry lesson. Today we start talking about Unit 7. Unit 7 is what most people think of when they think of geometry, because it is all about different polygons, different shapes. Before we start, I need to ask you a question. What is the sum of the interior angles of a triangle? Well, all of us know from previous units that the sum of all the angles, the interior angles of a triangle, add up to 180. But is this true for other shapes? Do we think that a pentagon, even as skewed as I drew it, would add up to 180? What about a hexagon? Overall, we notice that these shapes don't quite add up to 180. They actually have more angles in them than just 180 degrees. So what can we do? Is there a way we can break these shapes up to better understand how many degrees there are that make up their angles? Well, we can do something using the diagonals of a shape. We've talked about diagonals specifically when we were talking about concave and convex shapes, but the diagonals of a shape are what you get when you draw lines stretching across the figure from one vertex to another. Well, what do we notice that's weird about this pentagon now? Now it's made up of 3 triangles. And if each triangle has 180 degrees as the sum of its interior angles, we now know that the sum of the angles of a pentagon is 540, because 3 times 180 is 540 degrees. So, by splitting up the shape, we found that all pentagons add up to 540 degrees with their interior angles. We can do this with hexagons too. Let's say I take this hexagon and I make all these triangles. Once again, we see that we get the same thing. There's 1, 2, 3, 4 triangles, each adding up to 180 degrees. 4 times 180 is 720. So that's how many angles there are on the inside of a hexagon. Would this work if I did it with a shape with 8 sides, 12 sides, 500 sides, 1,000 sides? I can tell you this much. If I had a shape with 1,002 sides, I can tell you right away, without doing any math, that it's going to add up to 180,000 degrees, without doing anything here. So the deal is, there is actually a way to find the sum of the interior angles of a shape without needing to split it up into triangles like this, but using a similar idea. This is what our notes are going to be primarily about here. So first things first, let's start with diagonals. The definition of a diagonal is a line segment that connects 2 non-adjacent, meaning not next to each other, vertices. Anything that cuts across a shape that does not touch an adjacent vertex is a diagonal. We can always split up shapes into triangles based off of a diagonal. So this allows us to create a theorem. The theorem goes like this. Let's make a table of all of these values for the number of sides of a shape. So here we have number of sides. Here we have angle. We know that a triangle has 3 sides. It makes 180 degrees total. If we did this with a quadrilateral, a 4-sided shape, well, we make a diagonal across. It splits it into 2 triangles. So 2 times 180 is 360. It's 360 degrees. The pentagon with 5 sides was 540, because again, 3 triangles times 180 was 540. So I'll write that down. The hexagon with 6 sides had 4 triangles inside of it. 4 times 180 was 720. We start to see a bit of a pattern here. We're just adding 180 every time. This gives rise to the polygon interior angles theorem. This theorem says the following. The sum, meaning we add together, of the interior angles of a polygon is equal to n minus 2 times 180. Now, there are some asterisks I need to add to this. The first thing is n is the number of sides. And 2, this only works on convex polygons. Convex meaning that it doesn't have a spot that caves in. So if you were trying to find the measures of a shape that looks like this, you'd be out of luck. So that's why I was so quickly able to figure out how many angles there were inside of a shape with 1,002 sides. There is a little bit more that I'd like us to talk about before we move on. But this theorem, this theory here, is going to be super important. There is a corollary to this theorem as well. Remember that a corollary is like a theory based off of a theory. The corollary to the polygon interior angles theorem deals with the interior angle measures of a quadrilateral, like this trapezoid here. The corollary to this theorem says the sum of the interior angles of a quadrilateral, meaning it has 4 sides, is 360 degrees. There we go, 360. Let's take a look at exercise 1 and see what we can do. Find the sum of the interior angles of the figure. Now, there is an error with part A, and I wonder if we can spot why we can't find the sum of the interior angles of this figure. Well, this shape has spots that cave in like this, right? So we can't find the sum of the interior angles of this figure. That was unintentional, unfortunately. So I'm going to redraw the figure like this. We notice it has 1, 2, 3, 4, 5, 6, 7 sides. I'm going to draw a 7-sided shape. 1, 2, 3, 4, 5, 6, 7. It's just a redrawn version of this. If I have a shape with 7 sides, how can I find the sum of the interior angles? Well, the formula tells us n minus 2 times 180 gives us the number of sides, or the degrees of the interior angles. So, with 7 sides, this is telling us to do 7 minus 2 times 180. That's 5 times 180. 5 times 180 is 900 degrees. So the sum of the interior angles of a heptagon is 900 degrees. If we check with our table here, we can take a look. Oops, the table's over here. 6 sides, 720. If we add 180 to that, we would end up with 900 degrees. So, perfect. I want you to try parts B and C on your own, so pause the video and come back in just a moment to check your answers. How'd you do? Using the formula, we can find that this octagon has an interior angle measure of 1,080 degrees. This 52gon, a 52-sided shape, we have an interior angle measure of 9,000 degrees. Perfect. Before we flip to the back, I want to talk a little bit about something we've already talked about before. There are these words, equilateral and equiangular and regular, that we use to describe certain polygons. We know what equilateral means from the last unit. Equilateral means equal sides. It is a polygon whose sides are all congruent. Perfect. And the equiangular polygon, well, it means all the angles are equal. So equiangular means a polygon whose angles are all congruent. And in general, we refer to this when we're talking about a convex polygon once again. So a regular polygon is just something that combines those two ideas. It is a polygon whose sides and angles are congruent to each other. A polygon whose sides and angles are congruent to each other. So an example of a regular polygon is a square. In a square, we know all the angles are congruent, all the sides are congruent. It's a regular quadrilateral. Let's flip the page and take a look at exercise 2. Exercise 2 asks us to classify the polygon when the sum of the interior angles is given. In other words, we are now working backwards. We have the interior angle sum, and we're trying to find the number of sides. So, with regards to this, let's take a look. Our formula says n minus 2 times 180 is the sum of the interior angles, right? Well, if we know the sum of the interior angles, can't we just plug it into the equation? 900 equals n minus 2 times 180, for instance. I certainly think so. From here, we just need to solve algebraically. The easiest way to do this is to divide both sides by 180. These cancel out. We are left with 5 equals n minus 2. And don't forget that if you're trying to find the number of sides, you still have to add 2 to finish the problem. N equals 7. It is a 7-sided shape, therefore. So how do we classify it? What name do we give a polygon with 7 sides? Well, in Unit 1, we called that a heptagon. If you need to review your Unit 1 notes, that is in section, I believe, 1.1. Heptagon. I'm going to leave B for you to do as well, so feel free to try it out, but I will tell you the answer to B is a dodecagon, a 12-sided shape. Exercise 3 is asking us to find the missing angle measures in the diagram, then decide if the polygon is regular. Well, we have a polygon here with a bunch of angles known, but one missing. This is familiar-ish. We've dealt with this with triangles. Like if I told you this was 61 degrees and this was 49 degrees, you'd have to figure out what this missing angle is. But the difference is we knew that all triangles add up to 180 degrees. We don't know what all sides of this shape here add up to. But we can figure it out using our formula. So, how many sides does this have? 1, 2, 3, 4, 5, 6 sides. So we can use our formula to figure out what all these angles are supposed to add up to. 6 minus 2 times 180 will be that answer. 720 degrees is the sum of all the interior angles of this hexagon. So what that means is all the missing angles have to add to make 720. So we've got 145 plus 115 plus 124 plus 111 plus 118. And don't forget that x is also one of the angles here. So many people forget there's an x there. This is the formula that we can use to figure out what the missing angle is. Of course, all we need to do is add these all together. So 145 plus 115 plus 124 plus 111 plus 118 gives us 613. So we can rewrite this as 720 equals 613 plus x. How do we solve? Don't we just have to subtract 613 from both sides? We get the answer x equals 107 degrees. Perfect. It is now asking for us to decide if the polygon is regular. And we're not really given anything about the sides of the shape or whether or not the sides are congruent. But we do know that regular polygons have all equal angle measures. This is not a regular hexagon because of the angles. They're all different. They all have to be the same to be regular. I want you to take a second to pause the video and try out B for this one. It's going to be a bit tougher, so I'm going to do a walkthrough of it afterwards. But genuinely, pause the video and come back in a second. The reason why B is tougher is because we don't have any of the angle measures here, right? Or do we? First things first, let's not get ahead of ourselves. We need to figure out what the sum of the interior angle measures is supposed to be for this shape. So it's got 5 sides, it's a pentagon. We use the formula 5 minus 2 times 180. We get 540. So 540 is what all of these have to add to make. So we can set up an equation. 540 equals, but we have a problem. We don't have a label of x. We just have the missing angle measures. So let's call the missing angle measures x. This one's x, and since this one's congruent, it's also x. These angles we know are 90 degrees each. So what we've got is 3 90-degree angles, 3 times 90, plus 2 x angles, so plus 2x. This is what we can use to find x. 3 times 90 is 270, so we can subtract 270 from both sides, giving us 270 equals 2x. And when we divide by 2, we get that x equals 135 degrees. Nice! We found the missing angle measure. This one is also not regular, because while these angles are all 90, these ones here are 135 degrees. It's not a regular polygon if we've got different angle measures, so neither of these are regular. Perfect. Almost done, y'all. Let's talk about the last theorem on the first page once again. The last theorem is called the polygon exterior angles theorem. Now, we definitely need to review what an exterior angle is. We haven't talked about them in quite some time. An exterior angle of a shape. Let's say I've got our pentagon friend here. There we go. It's close enough. Let's say we have our pentagon. An exterior angle of this pentagon is what we would find if we extended the sides out in one direction, like this. Repeat this with all the sides. So in this case, I'm going clockwise. And what you will find is we get all of these angles here. This one, this one, this one, this one, and this one. Now the question is, what do we think these are all going to add to? And while we could try to find it all by hand, We can find the individual angle measures of all the angles of this shape and then subtract it from 180. That's a lot of work. I'd rather us watch an animation. So in the description of this video, I have actually linked an animation of exterior angles coming together so we can figure out the measures of them. I'd like you to watch it after this video. It really does help explain it. However, I want to talk about the theorem itself here. All of the exterior angles here are going to actually add to some number for every shape. The sum of the exterior angles of a convex polygon is 360 degrees. A crazy thing to say when we're looking at it in the notes like this, but I'm telling you, watch the video that's linked in the description. It will help you visualize why these all make 360 when we put them together. Let's flip the page and see if we can use this fact, though. So if we're asked to find x and we're dealing with exterior angle measures, it's sort of a little bit easier than the problems before. See, before we had to figure out this mystery sum of the angles. Exterior angle measures are always going to add to 360. So we can just go right ahead and say 2x plus x plus 67 plus 89. All four of these should add together to make 360. Well, we know that 67 plus 89 is going to give us 156. 2x plus x is 3x. So 3x plus 156 equals 360. We can subtract 156 from both sides. We end up getting 3x equals 204. And when we divide 204 by 3, we end up getting a whole number, actually. We end up getting 68. Solve for x. X is 68. If they asked us to find the missing angle measures, we would say that this one is 68 because it's x, and this one is 2 times 68, so 136 for 2x. Cool. I want you to try this out on B. Pause the video, and I'm going to provide an answer in just a second. How'd you do? In this case, x is going to equal 111. We're good to go. Last problem, and we're done with the notes for today, folks. Example 5. Example 5 is asking us to do something very specific. Find the interior and exterior angle measures for a regular dodecagon. A regular one. What that means is all the angles have to be the same measure, right? That's what regular means. So our goal is going to be this. Find the sum of the interior angle measures. And once we do that, since all the interior angles themselves are going to be the same, just divide by however many sides this is. Spoiler alert, it's 12. Then we can repeat something similar for the exterior angle measures, knowing that exterior angles are always going to add up to 360. So let's do it. To find the interior angle measures of a regular dodecagon, we should plug in 12 to our formula to find out what we're working with, to find out how many degrees we have in total. 12 minus 2 is 10, times 180 is 1800. Since there are 12 sides, we can say that one angle is going to equal that entire sum cut up into 12 different angles. 1800 divided by 12 is actually just going to give us 150. So we found it. Each interior angle in a dodecagon is 150 degrees. You've got 12 150 degree angles. We can even do something similar to the exterior, but we don't need this first calculation. We know that 360 is the sum. So if we're trying to find one of these 12 angles, we take 360 and divide it by 12. That's going to give us 30 degrees. Another fun fact you may have noticed is that these two add up to 180. They're supplementary. So that's a good way to check your work. If you can find one of those answers, the other one is going to be supplementary with it, adding to 180. That's it for the notes tonight, everybody. Thank you so much for listening, and have a fantastic rest of your day.